Chapter 11, the t-test for two related samples. Part 3. In many repeated measures in matched subject studies, the researcher has a specific prediction concerning the direction of the treatment effect. For example, in the study described in example 11.1, which we just went over in the previous video, the researcher expects the level of perceived pain to be rated lower when the participant is cursing. This kind of directional prediction can be incorporated into the statement of the hypotheses, resulting in a directional or one-tailed hypothesis test. The following example demonstrates how the hypotheses and critical region are determined for a directional test. So I'm going to use the information that was presented in example 11.1 and walk you through example 11.3 of the text, recognizing that the difference is now that we are testing a directional or one-tailed hypothesis opposed to a non-directional hypothesis. So the notation for the research in null hypotheses will be different, and this is what we will see, and I will state it verbally but also include the notation. So the null here is saying that the population mean difference will be less than or equal to 0. And the research or alternative hypothesis indicates that the population mu difference is greater than 0. So that's just one example. So we'll talk about what it looks like with this specific research context that we saw in example 11.3. And we'll find the critical region using a specified alpha level. So again, using the data that was presented in 11.1, the null hypothesis would state the following. Pain ratings will not differ or will increase when participants use swear words compared to neutral words. And the alternative or research hypothesis states that the pain ratings will decrease when participants use swear words compared to neutral words. I always find it easier to write the notation for the alternative or research hypothesis first because that's the direction that I'm focused on. So we would expect that the mean difference is going to be less than 0 because we expect that when we take, again, our difference scores, which is calculated by taking condition 2 score minus condition 1 score, if we expect the second condition, which in this case was the use of the swear words, to be lower, then our x2 is going to be a lesser number, and we subtract a larger number, and that would produce a negative number. So the average difference we would anticipate would be less than 0. We would anticipate that it would yield something negative. And the null hypothesis would state that the population mean difference, and we use the opposite sign, is greater than or equal to 0. So again, it will increase or not differ. So again, given that we're calculating D by taking our second condition minus our first condition, the null is stating that the swear condition, condition 2, is going to produce higher pain ratings scores compared to the neutral word condition. So again, it would produce a mean difference, an average mean difference that's positive, greater than 0, or we would expect no difference between the two conditions, which is denoted by the equal sign. So that's step 1 of our 4-step process in computing a t-test, or going through the steps of a t-test, in this case a t-test for two related samples. Step 2 is to find the critical region. So again, this is where it would differ again compared to example 11.1. Now we're using a one-tailed test, and in this case they've identified alpha to equal to 0.01 or 1%. As we demonstrated in the independent measures T statistic, the critical region for a one-tailed test can be located using a two-stage process. First, we look at the sample mean difference to verify that it is in the predicted direction. So I cited from the previous video in example 11.1 what our mean difference was equal to, and it is equal to -2. Given what we just stated for the null and research hypothesis, then we can affirm that it is in the direction that we hypothesized. So if the change is in the correct direction, then the question is whether it is large enough to be significant. However, if it is not, then the treatment clearly did not work as expected, and you can stop the test. So in other words, if let's say mu d was equal to +3, then we wouldn't need to go any further, because if it's directional, our critical region is going to be set on that side of the mean difference that represents the null. In this case, it's 0 in the center. And in this case, the researcher alternative hypothesis indicated that we expect a decrease in the second condition, thus producing a mean difference that would be negative. So again, if our mean difference was positive, end of test, no need to go any further, because we know it's not going to be in the critical region, because it's not even the same side of the distribution that we had anticipated. But in this case it is, so now we can find our critical t-value given the parameter set of alpha 0.01, degrees of freedom of 8, and using a one-tailed hypothesis process. So here is our t-table, and we're going to use the first tier, which represents a one-tailed or directional hypothesis. We used alpha at 0.01. Our degrees of freedom are equal to 8, so we're just going to see where these intersect with one another. And we find that it's equal to 2.896, and it would be the negative version of that critical t, because again, we anticipate a decrease given condition 2 compared to condition 1. So now we can set our critical region value at negative 2.896. Again, we don't need to do anything on the right side or the right tail, because we are focused on the negative side of the distribution. Now we have already, step 3 indicates that we must compute the T statistic, and we already did that in example 11.1. So I'm just going to walk through the statistics that we did calculate and then produce our T value again to make our final decision. So just as a review, these are the values that we computed in the previous video that we saw in example 11.1. So the mean difference from the sample data was -2. The variance of our d distribution was equal to 4. The estimated standard error of the mean difference was equal to 0.667. So our t equation for the t-test of two related samples is t is equal to the sample mean difference minus the hypothesized population mean difference over the estimated standard error of the mean difference. So let's replace variables. -2 minus 0. Again, this is representative of the null hypothesis, mu d, and over 0.667. And we computed this previously, and that was equal to 2.99 something, and we rounded to -3. That was our t-value. So let's redraw our distribution and draw our conclusion. So again, we are testing the null that says the mean difference will equal 0. We set the critical region at -896. We set our critical region in the negative tail, and now that we can assess where this resides and determine if it falls in the critical region beyond our critical t, and in fact it does. And so we are happy, and we get to reject the null that stated that we would anticipate an increase in pain, perceived pain, or there would be no difference. So again, we expected, the null was saying it's going to yield the mean difference over in this area, or it was going to be equal to 0 in the center. we now have the data to show that the mean difference produced something that had less than a 1% chance of occurring if the null were true. So again, that gives us reason to reject the null hypothesis, and we feel confident that this study illustrates that individuals are able to decrease the perceived amount of pain they are experiencing when they are allowed to use curse words as a way of dealing with that particular pain. In other words, those curse words help divert the pain that they're experiencing or perceive at the moment. So now we'll write our concluding statement using the statistics that we just calculated for this one-tailed hypothesis test. So the conclusions for this particular test would be written in this format. So our conclusion, we reject the null. Results indicate that pain ratings decrease when participants use swear words compared to neutral words. We used a t-test to test this hypothesis with degrees of freedom equal to 8. Our t statistic was equal to -3. The probability of obtaining that t-value if the null were true is less than a 1% chance, which is where this p less than 0.01 comes from, or that's what it illustrates. And we engage in a one-tailed test. So we now have learned the skill that if we do conduct a one-tailed test, we want to cite that in our concluding statement. And again, the reason for doing that is normally a one-tailed test is easier to pass if the alphas are equal. In this case, we went from a 5% alpha for non-directional test to a 1% for directional. So we didn't see that normal change of a decrease in the critical t-value. But if the alpha levels are equal, then a one-tailed test is going to have a critical value that's closer to the middle, closer to 0, making it an easier test to pass. But in this case, we went from 5% to 1%. Nonetheless, we want to cite our probability statement indicating the chances of obtaining that T statistic if the null is true. And again, the one-tailed statement is important to convey information to the consumers of the research that you have just engaged in. And that concludes this video of Chapter 11. In the next videos, we'll be talking about the advantages and disadvantages of the independent measures t-test compared to the related samples t-test, and talk a little bit about the assumptions and variability that exists, or is minimized, I should say, in a repeated measures t-test. Before we go on to the next video, however, I do want to make a few corrections. So notice that I corrected the capital letter P here. It should have been a lowercase, and inserted a comma here. Just want to be more accurate in the concluding statement. So I noticed that when I was reading it to you. So again, this now concludes this lecture video for Chapter 11.